Almost, not quite. All right. So to draw dot structures, so drawing dot structures, we need to know what? We use the number of valence electrons. Valence electrons as dots. And what we're going to end up with, give me a second here. I just have a few kind of set up today, but I have other kits that we're going to get out. So, what's the matter?
It looks like you put V twice, but one of them is used. I know, but it looks like it says.
All right, anyways. So when we have dot structures on paper, you can't see geometry, but what you need to know in AP Chem now is the geometry of this, okay? So this is one example of a dot structure that you need to know, that this is called tetrahedral, and you need to know the bond angle between all of them. This is called linear, and you need to know the bond angle there. That's easy, that's 180. This one we need to learn as well. This is called octahedral. You need to know the bond angle, but there's two different bond angles here. There's this plane, and then there's this plane, right? So this one and this one could or could not be the same. In this case, it's the same. They're both 90. But if you start taking these apart, so if we have, actually, sorry, where's the, what is on it? That's freaking me out. If you have just 3, that one's messed up. I have the wrong attachment there. But if you have 3, the geometry changes. So the way these dot structures on paper look are very different than in real life. So we're going to try and learn, we're going to learn how to draw the dot structure, but then relate it to the geometry. So if you have 4 atoms, they are going to spread themselves out as far away from each other as possible. That's where these angles come from. If you have 3 atoms, they're going to change.
Sorry for this last interruption. At this time, can you please send boys in grades 10 through 12 who need a physical to the nurse's office?
So I'm going to give you some practice problems once we get into this here, and I'm going to get the kits out because this, I thought that was the right one. It isn't. But if you have, 3 atoms, it's going to look kind of like this. They're going to get perfectly spaced apart. So that angle is different than if you put 4 in. So 4, there's a different bond angle than 3. Okay? And then if you have 2, it looks like this. So it actually, initially, it looks like it's going to be kind of an easy thing, but then we start throwing in electron pairs. So if you have 4 atoms, but then you have a lone electron pair, then that screws up your angles as well. So I'm trying to just kind of give you an overview of what we're doing and then how we're going to be using these kits and actually dots and toothpicks. But let's start out very simple. Do we know how many valence electrons are in each group? You need to memorize that.
Yeah.
So 1 has 1, 2 has 2. The middle doesn't matter a whole lot. And then 13 has 3, so 3, 4, 5, 6, 7, 8. So that's easy. So I think you should know enough from last year or the year before to kind of pick this up pretty quickly. Let's start with carbon. If we draw a dot structure for carbon, just carbon, what do? What should it look like? It's 2s2, 2p2, so it should look like this. Should look like that. That's not how it looks because carbon actually hybridizes. We'll learn that later, and that's the dot structure for carbon. So if we want to draw a dot structure for methane, so go ahead and copy this down, even though it's very simple. This is methane. That would be this right here. 1 carbon, 4 H's. And that's called tetrahedral. I got a sheet that gives you all the names of the geometry and the bond angles. I also have a program that we can mess with here. Probably not today, because today we're just going to practice drawing them, like labeling dot structure. So this is how I do it. I do 1 dot for one element and X for the other. A lot of teachers just use dots all the time, so they would do that. Either way, it doesn't matter. You could use 2 X's, 2 dots, an X and a dot. Doesn't matter. I just like to do it because then I know this belongs to carbon, that belongs to hydrogen. Not belongs, but it came from. That came from carbon, that came from hydrogen. And remember, if we're doing covalent bonds here, so that's 1 bond, 2 bonds, 4 bonds, all single bonds. What are they doing with those electrons? They transferring or sharing? Sharing. Covalent, they share, right? So, so that's a very simple example. What about the dot structure for carbon dioxide? So you have carbon with 4 dots. How many dots does oxygen have? 6. So we put 1 here. There's an oxygen there. We put 1 here. Oxygen there. So that's 1, 2, 3, 4, 5, 6. I always put 1 dot, 1 X around kind of the 4 sides of a square. So imagine there's a square around it. 1, 2, 3, 4. Before I start pairing them up. Now, when we're doing dot structures here, what's the rule? Anyone remember? There's one kind of important rule. Well, there's a whole bunch of rules, but I'll try and summarize it. No one remembers the rule. You cannot have unpaired electrons. So what's an unpaired electron? That one, that one, that one, and that one. No such thing. We don't leave them unpaired. They have to pair up. So that's one important rule. So if you want to write it down, you can. But I think you'll just pick it up as we go. You cannot leave them unpaired. So what do? Make a double bond. So we take this carbon's dot here, bring it in here, and this X, bring it in there. We take this dot here, bring it in there, this X, bring it in there. So it looks like this. X, 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 X. So that's CO2's dot structure. Now, to kind of finish it, technically the bonding electrons you can show with lines. So CO2 really looks like this. So one thing I want you to understand is when we do this, why do they look the way they do? Why did I move, I didn't do it here, but why did I take these 2 X's from the side and put them on the bottom here? Dots here, dots there, dots here, dots there. Because whenever you draw these things and whenever you put a model together, whether it's with toothpicks or whatever, the atoms and electrons always want to be as far, bless you, always want to be as far apart as possible. That gives them the lowest energy configuration, which means the most stable. So if these 2 electrons here, this electron pair are here, it's closer. They're closer. They don't want to be. So they get as far away as possible. So that's something that's an overall overriding theme here. Whenever you're drawing these structures, they always get as far away as possible. That's why carbon dioxide looks like this. It's linear. It's not going to look like this. Okay, that's not going to be CO2. That doesn't make any sense, because these want to be as far away from each other as possible. So CO2 is what we call linear. It's a linear molecule. Now, if you count the electrons around all 3 atoms, how many are there? What is it? Somebody said no? 8, yeah. 1, 2, 3, 4, 5, 6, 7, 8. So all of those electrons oxygen gets to own, gets to have. All of the ones in the middle, carbon has 1, 2, 3, 4, 5, 6, 7, 8, and then all the ones on the outside here, oxygen gets. So they all have a complete octet. That's okay to say that. So when you're drawing Lewis structures, we want to try and get an octet on all the atoms. Okay? But there's always 2 ways to look at it. You have your central atom and then your exterior atoms, or your outside atoms. Okay? Sometimes you can't always have an octet on all the atoms, so it kind of depends. So we're going to get some examples and see if it makes some sense. But questions before I move on? Hopefully it's not too difficult yet, because we're just taking baby steps here. No questions. All right. Okay, so the next one we're going to do, and we'll try and learn the rules here. I'm not a big fan of writing the rules down, because that makes it more complicated. We just do sample problems. One thing that I want to tell you too is that you should always double check yourself. What does that mean? So with CO2, how many dots should we have total? How many? How many dots total in CO2? How many dots should we have, or X's, dots or X's? Here? Try again. So we have one C and two O's. How many dots does carbon have? It's all right. Let's do one at a time. Carbon has 4. Oxygen has 6, and there's 2 of them. So 6 plus 6 is 12. 12 plus 4. 12 plus 4 is 16. Sorry, I think I caught you off guard there. So how many should we have? 16. So count when you're done. Do we have 16? Yes, we do. We have 4 on each oxygen, and then we have 8 in the middle, right? 1, 2, 3, 4, 5, 6, 7, 8. Right. Does that make sense? Okay. So that's another thing you can check at the end of these dot structures here. All right. So my last rule here, I'm just going to read it to you. After we write the structure, we count the dots. We got our bonds and everything. If the central atom does not have 8 electrons, try to add a double or triple bond using the lone pairs from surrounding atoms. All right, so we did that. And then just count. Make sure you have an octet around your atoms if possible. So let's try another one here. So hydrogen cyanide. Give me the dot structure for hydrogen cyanide. HCN. So again, make sure you have all the proper number of dots. Use the double and triple bonds if you need to. They can't have any lone pairs. I say lone pairs. You can't have any electrons by themselves. I'm going to have you do another one here. I got to get the, so HCN, do HNO3, and then over here we're doing BrO3 minus. So we're going to jump right into the squirrely ones right away here. So this one here, I want N is central, and the, what did I say there? Yeah, the N is central. Oh, I kind of have to give this to you here. No, I don't. N is central, and then H is on an O. I don't know why I did lowercase. And then BrO3 minus gets right into the weird ones where, well, you'll see. What's that minus sign mean up there, Earl? Very good. What else does it mean? So what does negative mean? Right, so there's an extra electron in that dot structure. So if you're just counting up the electrons from 3 O's and a Br, you need to add one more for that minus. if you want to compare with neighbors, you can do that.
Wait, what did you just say?
That this, you're going to have one more electron, one extra. So if you do, Br has 7 and each oxygen has 6. So 6 times, or 6 plus 6 plus 6, that's 18. 18 and 7 is 25. But with that minus 1, that means there's 26 electrons.
Double bond all three of those. Br has 6, and then you have
Are we done yet?
what? 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 Nitrogen has 5. 2. There's no N. Br has 3.
Does anybody want to come up here and draw them?
But it's a single bond. I'll draw one.
Who's drawing one?
I'll do it. Yeah, it's okay. Wait, but that's a,
Marcy, come on up, pick one. Who else wants to draw one? Liam wants to do one.
No, I'm gonna do the other.
Which one are you doing?
H903.
Which one are you doing? Okay. Okay. So, HCN. Here's how we make sure if we're right at the end. Okay. Again, we count all the dots. So how many should we have here? 4, 5, and 1. What's that? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Okay. Now I'm just going to rewrite it so I have the lines here. So we have a triple bond with an electron pair there. Does everybody have a full valence shell? We say complete octet, but hydrogen has 2. Carbon has 2, 4, 6, 8. Good. Nitrogen has 2, 4, 6, 8. We're good. Now just to give you a little heads up, nitrogen down the road will have some odd electron compounds, meaning it won't have an octet. It'll have one electron by itself, bless you, which of course is an exception. There's always exceptions. But for the most part, we're looking to pair them all. No. Hey. Yeah. Yeah. All right. Slade, they need you to sign something real quick down in the office. All right. So did you have this one right, Slade? Slade?
What?
Did you have this right?
Yeah.
Good. What about this one?
Yeah.
It looks just like that?
Yeah.
Okay.
I didn't get that one.
All right. Well, I'll hustle up. All right. So this is correct because everybody has an octet or full valence shell. We're going to learn these things called formal charges today. A formal charge is a way to check to make sure you're right. So it's based on how many valence electrons it has versus how many it's bonding. I'll explain that. So it's actually a check. So it makes it a little bit easier to really know if you're right or wrong. Okay. Now, if you look over here, nitrogen central, and so that's good. All right, so 2, 4, 6, 8, 10. So if we have 10, probably something's wrong. We're looking for 8. So what could we do different? Let's just start from the beginning. So if we have nitrogen, 1, 2, 3, 4, 5, oxygen, let's see, looks like this. Here's my hydrogen, here's oxygen. Okay? So that's like the beginning before we start making double bonds. Right? 1, 2, 3, 4, 5, 6 for oxygen, 6 for oxygen, 6 for oxygen, 5 for nitrogen. So right now, these two look good. Right? 2 here, 8 around oxygen, so let's not mess with that. Right now we have 1, 2, 3, 4, 5, 6, 7, 8. 8 there. Nitrogen looks good. 1, 2, 3, 4, 5, 6, 7. So that's not good. 1, 2, 3, 4, 5, 6, 7. That's not good. So one little trick that I do that I haven't taught you yet until this example is I will, and you can do this, you can move dots wherever you want. So I can take these 2 dots, put them wherever I want. I can put one, don't do this, just watch. If I put one here and one here, now everybody has an octet except nitrogen. So 2, 4, 6, 8, let me back that up for Slade here. So Slade, if we look here,
Yeah.
this nitrogen has 2, 4, 6, 8, 10 around the nitrogen, so we got to fix that. So here's how we fix it. So we start over, all the dots and X's are in the right spot, nothing's happened yet. I'm going to take these 2 dots, I'm going to put one here, and I'm going to put one here. All right, we can do that. You can do that, you can move dots around wherever you want. I could take these 2 dots and put them right there if I want. Doesn't matter, but as long as everything works. What does that mean? 8 here, 8 there, 2 there, 2, 4, 6. Well, if I take 2 and put them here from one of the oxygens, then they're not going to have their octet. So what can we do? So Marcy was very close. She picked a hard one, so I commend you on your effort of picking the hard one. So what do you think? Let's fix it. Well, it can only have 8, so what do we need to get rid of? You gave it 10. That won't work.
So get rid of the double bond.
Get rid of one of the double bonds, right. But instead of just erasing one, let's see how that really affects it. So right here, 8, 8, 8, 2, we're good? If we make one double bond, and it doesn't matter where it goes, either here or here. Let's put it right here. We make one double bond. What does that really mean? You need one electron from nitrogen, one from oxygen. So I'm going to take these, and I'm just going to put them here. So now that's my double bond. So instead of this being a double bond, that's now a single bond with a pair here. And now we're done. Now everybody has an octet, and that's more stable with 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and then 2. So she just had one too many bonds. And that's why we're learning and why we're practicing, obviously. Okay? So really go by the 8 rule for most of the atoms. Okay? Hydrogen obviously can't have 8. So again, I'm going to teach you formal charges here in a minute, and that's going to kind of help you realize, oh, I should only have one bond there. So I'll maybe come back to this to kind of explain it. Does that make some sense? So if you're still a little foggy, I get it, right? We just started this. But by the time we're done with this topic, everyone will be a pro at this, I promise. All right. So the structures here, HCN would actually look like this, linear. Okay? That would be HCN. And how do I know that? Well, because there was no electrons on the carbon. So this, if there's no electrons on the carbon, it looks linear. Because those two atoms there, the N and the H, get as far away as possible. That one, I don't really have a geometry for, not really. Technically, I guess it would look like this. That's hard for you to kind of visualize, but the nitrogen here, one OH would be going up. So this OH may be going up. This O and that O are kind of going down, and that would be 120 degrees between each one. That's like the most stable configuration for that. So that would spread out the bonds to be, it's called trigonoplanar, is what that's called. Okay, so we'll get to that down the road. All right, and BrO3 minus. So the problem here is what? Bree, what's the problem with Br? How many dots does it have? 7. 1, 2, 3, 4, 5, 6, 7. So I'm going to take one oxygen and put it here. Now what do we do? Remember, everything you learned, a lot of it was a lie. We said in Regents Chem, if there's a paired electron pair, it cannot bond there. That's just flat out wrong. Okay? It can bond. It has to bond because this exists. Bromine, it's the bromate ion, BrO3 minus. So it actually does bond. And it doesn't matter where you bond it. So X and a dot represents a bond. So I'm going to put my other one on one of these dots, maybe right here. So there's my other oxygen. Where would be the most stable spot to put it if I'm putting one there? So maybe above or below, right? So we're trying to actually form this. So we're trying to form it. Okay? On paper, it really doesn't matter how you draw it as long as you can answer geometry questions moving forward. So on paper, it's not a huge deal if you draw it a little bit weird as long as you know the geometry. And again, we will go over that extensively. So I'm going to put one there. So this dot and that dot are now by themselves. They're unpaired. We don't want that. Now let me finish the rest of the dots here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is how I always draw oxygen. I don't know if you want to do it the same way as me, but I always do the pair on top and bottom, and then those I leave by themselves. It just seems to be easier when you finish your dot structure that they're already together. But it's really up to you. So anyways, that's what it looks like without. Now we have an electron. We have a little E minus here waiting in the on deck circle. Okay, ready to get in. Okay, my chem teacher used to always say it's a bat out of hell. I don't know why, but he would say it comes from a bat out of hell. I don't know. But anyways, on deck circle makes it a little more appropriate at this point. But so these two dots are by themselves, so I'm going to pair them up. So I'm just going to put them right here. You can do that. You can do whatever you want with these dots as long as what? It's stable and you get a full valence shell. You can do whatever you want with these dots. Now I have Br with how many dots? 2, 4, 6, 8, 10. I don't like that. Oxygen has 7. 1, 2, 3, 4, 5, 6, 7. 7, 7. So let's take these two dots. So my thought process is first pair them up. Okay, so I'm trying to teach you in steps. Really what you do when you're good at it is you know that they're not going to be there. You just take them away immediately. But, so they were there. What do you want to do with them, Justin?
Give them one of those.
Yeah, so one of those dots, let's go right here. And then one of those dots goes right here. So now we have 3 out of 4 atoms that are stable. 8, 8, and 8, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. This oxygen only has 7. Don't forget our friend. On deck circle, where does he go? Right up here. Right there. That's the dot structure for Br03 minus. Everybody has 8, 3 single bonds. However, here's how you draw it. So again, this is what we're looking for. We're trying to space it out to get the most stable configuration, but you don't have to really worry about it on paper. I'm going to draw it that way because I want to show you the right way to do it. But if you were to draw something that looked like a T, like 2 O's and an O, that's fine. But I'm going to do this. O here, O there, O there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's your dot structure for Br03. We are almost done. Because it is an ion, this is important. You need to do this. You put brackets around it, and you put -1. You will lose points if you don't put that -1. If you forget the brackets, I think that's probably okay. It's okay with me. I'll give you points. I'm pretty sure the readers on the AP test will also, forget the bracket. That's not really showing much knowledge, but you got to have that -1, indicating there's an extra electron there. Wait, what did I forget? Oh,
Bromine has.
yeah, bromine has one there. Sorry. See, I almost made a mistake. So always double check, count your dots. I forgot those, these two right here on that BR. Now, I'm telling you that it looks like this because you have 3 oxygens, but these screw everything up. So it actually doesn't look like that. It looks more like more like that. Here's your electron pair. The electron pair up top smushes the bonds. It repels the bonds, so it kind of looks like a T. Kind of. So we'll talk more about the shapes down the road, but that's a more complex dot structure. More complex dot structure. Now, I'm running out of time, which is unfortunate. Chapter 9, 43, 44 due tomorrow. 43, 44, and I believe there's multiple parts. I think it's just this, drawing structures. Before the bell rings, I'm going to explain formal charge real fast here. Actually, here, you know what? I'm going to use this as an example, so I don't know why I erased that. So try and just pay attention here, stay with me. So, the formal charge. And this technically, the AP test says it cannot ask you questions specifically about formal charges. So that's good, but I will teach you because it helps you draw structures. So here's the rule. Formal charge. It's the electrical charge difference between valence electrons in an isolated atom and the number of electrons assigned to that atom in a Lewis structure. Best way to figure it out. Dang it. All right. Tomorrow we'll talk about that. Yes.
But I need them back by my central period. If that's possible.
Yeah.
This is like, I feel this thinking out right thing.
So 1024.
Yeah, I didn't have that dated. So.